Hi, and welcome to our presentation on the interoperability between 3D slope stability models and interferometric radar data. I'm Neil Barr from Gecko Geotechnics, and I'd start by thanking the Sri Lankan Geotechnical Society for the opportunity to present this paper. I would also like to acknowledge our co-authors, Alison and Tharma from Rocscience, Nicolo and Lorenzo from IDS Georadar, and Sinaka and James from Newcrest Mining. Rock slope engineering is all about ground failure risk management. In a practical design and execution stage, we would undertake site investigations to develop a geotechnical model, which has some limitations and uncertainty. We'd then select a design acceptance criteria and do slope stability analysis and design the slope. Once excavations begin, we would control them and monitor them. We would also reconcile some of our assumptions and reassess the design. Let's talk briefly about interferometric radar. Synthetic aperture radar, or SAR techniques, use broad fan beams to illuminate the same target multiple times within the same acquisition or scan. For each pixel of a SAR image, a phase value is measured along the line of sight of the radar. By comparing the phase difference of subsequent acquisitions, it is possible to detect small variations that account for sub-millimeter deformations of the target. That is, we can monitor sub-millimeter accuracy deformations. A SAR sensor can move along a linear or circular path, as shown in the diagrams here. Synthetic aperture radars have the ability to scan long distances, up to 5 kilometers, and large areas. The data collection and processing frequency is less than 2 minutes irrespective of the scan area. This is excellent for short-term or tactical monitoring, as well as long-term or strategic monitoring. The systems have various alarming capability to alert geotechnical engineers and operation supervisors of emerging threats. SAR systems are also highly reliable from a mechanical perspective, since they have very few moving parts compared with other radar systems. As an example, in the figure on the right you can see a large-scale slope failure on the left, as well as the heat map from the synthetic aperture radar. This is long-term monitoring of a 100+ meter high slope failure that's in a residual state with ductile deformation. Further up in the slopes on the next pushback are some local, small failures that are occurring and are semi-brittle or brittle in nature. These are all identifiable with advance warning, and these can be very small, with heights of 3 to 5 meters, identified from a distance of about 2 kilometers from the target. Two-dimensional limit equilibrium analysis using cross-sections has been the most popular slope stability analysis method in the last 20 years, mainly due to its ease of use and fast calculation time. There are several well-known and understood method of slices techniques, and calibration and experience from years of use is available amongst most practitioners. In the last 5 years, there's been a shift from 2D to 3D limit equilibrium, basically because of improvements in computing and software capability. But the major change is really just 3D geometry. That is, 3D geology, 3D structure, slopes, and groundwater. The method of slices now changed to method of columns, and techniques include Bishop, Yanbu, GLE, and Spencer. Let's move on to a case study. This mine is hosted in a collapsed volcano that is geothermally active, with ground temperatures exceeding 130 degrees in some places. Pore pressures are a combination of steam and water. Rock masses are highly susceptible to weathering, and the environment is tropical, with in excess of 5 meters or 5,000 millimeters of annual rainfall. A 36 meter high slope failure that's 100 meters wide occurred at this mine, and you can see that there's a lot of vegetation in the slope. Radar monitoring was used. The IBIS FM system was used at this site, and it could actually see through some of that vegetation. Linear acceleration in the onset of failure was identified, and a pit evacuation and closure occurred approximately 10 hours before the actual failure, so no people or equipment were put at risk. Here's a figure showing the ground displacement from the synthetic aperture radar. You can see the red hotspots, they're indicating areas of high movement, and at the bottom you see a linear acceleration in the deformation versus time plot. An investigation into why the failure occurred commenced, and it began with a review of historic data. A borehole fitted with an inclinometer actually went through the failure. In the drill core, which you can see in the center of the screen, a fault zone was identified between 17 and 23 meters with an unknown orientation. Shearing was identified on the inclinometer, which you can see on the right hand side, at a depth of 19 meters, which coincided with the fault zone in the core, or in other words, a sliding fault plane was identified. Mapping data elsewhere in the slope, within a couple hundred meters, identified clay-infilled shears, possibly a set of faults. Prism monitoring was also available at the site and identified similar deformation trends to the synthetic aperture radar. The movement coincided with high rainfall over a 5-day period. There was no evidence of the failure between 2 weeks and 1 month prior to it occurring. This figure combines prism vectors and radar deformation data in a software called Gem4D. In the center of the screen you can see prism data showing differential settlement related to slope deformation. At the base of the slope, or the toe, the radar data is showing high deformation, which is related to the failure breakout at the base. The stereographic projection shown here displays prism vectors. An average dip direction of 307 degrees was found, and a dip of 17 to 55 degrees. Based on this, the fault orientation was likely to be related to the lowest dip identified, 17 degrees, because that was the movement before downward movements or surface settlements began. Similar low-angle structures have been identified elsewhere in the slope. So, a 3D limit equilibrium model was developed. Input parameters included the modeled fault plane based on its location from the inclinometer and its orientation based on the prism vectors. Pore pressure was assumed to be fully saturated following 5 days of heavy rainfall, and rock mass strengths were adopted from previous studies. After several iterations relating to the fault shear strength, estimated parameters were found to have a cohesion of 25 kilopascal and a friction angle of 20 degrees. This corresponded to a factor of safety of 0.985, which is within 2% of 1, or equilibrium, using the Spencer method of columns. The modelled failure, which will be shown on the next slides, had an excellent spatial match with the synthetic aperture radar data. This model was later validated with finite element, but that's a presentation for another day. Here you can see the lowest factor of safety surface, shown in 3D. The fault plane is semi-transparent, and basically the contours show a column volume or relative slip surface depth. In this slide you can now see several slip surfaces, each with low factors of safety below 1.3, naturally around that fault plane, with the pink highlighted area being the lowest factor of safety, with a factor of safety of 0.985. Overlaying the survey data based on the actual failure volume, you can see a good spatial match in this slide. And finally, comparing the 3D limit equilibrium with the interferometric radar data. You can see a lot of the deformation was seen at the base of the failure with the hotspots and around the right hand side. An excellent spatial match was attained by the model. Some concluding remarks. Radar can be used for both safety critical monitoring and stability model validation. 3D slope stability modeling is rapidly becoming standard practice and complementing and improving upon understanding from 2D models. Interoperability between the 3D stability models and the radar enables qualitative model calibration, which in turn reduces model uncertainty and improves reliability. Thank you for watching our presentation. Should you have any questions, feel free to send me an email, neil@geckogeotech.com.